Okay, my friends, this is going to be more fun than I have had in a very long time. This is what they call a muon, which is a high-speed particle that has no apparent interactions. This is the electron, and it creates electron showers. Now, they call them muon neutrinos and electron neutrinos. They come in at high speed, and they crash into particles, and they create these effects. This does nothing whatsoever. This explodes like a bomb. I have seen these. We can create these at will. All right, I just want to make it clear. Not only have I done all the experiments, I did all of the, I did 50 years ago, I did all this research about how the different interactions in the orbitals and so forth, and I really came to the conclusion that at the end here, that in this particular paper, that it's evident that Coulombic forces are the nature of atomic and molecular behavior. Coulombic is positive and negative, not just negatives and not just positives. And then I went through all of the different principles and all of the different things that they claimed were happening. I tested them. I didn't just take somebody's word for it. I went through all the different experiments, Millikan's oil drop experiments, and then. I mean, this is very serious. I did some serious work to verify what I was doing made sense, and it didn't make sense. And not only did I do that, I did the actual, in the lab work where you test the different, how it ends up being electricity. Let me put it this way: anytime you have heat or any atomic reactions, it ends up in electricity. Electric power. It always ends up in electric power. And anyway, this is, it's not something I'm totally unfamiliar with. Okay, Roger once again, Mudfossil University, and I am going to show you once again the wave nature of light, then the particle nature of light when you do through a venturi, and then the actual photons of light, and then the fact that light spins to the right, drifts to the left, compacts as it accelerates forward. This is what the actual particles are like. Now, there's two different types of electrons. This is an electron that is in the concussion state. A normal electron would have the dark matter in the center and the red-white matter actually around it. Now, there's 1,837 of these little electrons, which are dipoles, within a proton. So 1,837 of these make a proton. This is light. This is light. It's the smallest particles that exist, the light. Now, we not only show the light accelerating, and it is a particle, we show that the particle is this, and then I can show the particle actually separate as it concusses. We see the photon here, which is the particle right there, and then we will see it separate. This is Mudfossil University. Now, this right now is the only place you're going to find electron flood theory. And it's the only theory that makes sense in the atomic world. Einstein was wrong. I'm sorry. You can see the particle accelerate. You see it's a particle. Right there, it's done. Plus, entanglement. I'm going to show you what entanglement is. It's right there. And they can de-entangle and then re-attangle, but you can only... I could show you the reason that entanglement is actually kind of nonsense. There's the particles right there. There's the black one, does absolutely nothing. There's the white one, explodes like an atomic bomb, and I will show you. What I showed you before was light and its particle form as a photon. This becomes dismembered light, literally dismembered. The black ball rolls away in its black ballness. It doesn't change. It doesn't do anything. Absolutely nothing. It doesn't emit light. It doesn't absorb light. It doesn't concuss. It just gets the hell out of the way. And the white one explodes like a bomb. Exactly what CERN is looking for. And here it is. And these are the smallest particles that exist because they're from light. It's as simple as that. CERN is making a big mistake by using these huge colliders and using huge particles, because they're looking for the smallest particle there is. Why don't you start with light, like we did? That's the smallest particles we can find at this moment, although I do have one that is smaller. All right, I believe I showed you the red ones that are exactly the same as the green. The green, it just is spinning faster and it has more momentum of the spin, which creates a brighter glow as it impacts. And that's all it is, it's impact. And here they come. Now the red ones, I have red ones down here somewhere. Here. What's happening here is the red ones are coming in, and you can see there's something going on here, but it's just sort of blurriness. And then they start to show their trueness here, what they exactly look like. Just like the green one. You saw the green one. Well, this would have been the green spinning, and then all of a sudden the green one showing up. Exactly the same. Now, what happens here? Over here to the right is the venturi. At this point, they get glowier and glowier, and then it just explode here, and they fall into pieces. Now, what has happened here, I don't know. They're in the separation phase, I guess. And here, they are completely separated, as we saw in this first shot way up here at the top. All right, so this is where they hit. That's the venturi right there. They were together right here. They were up and down, back to back, black and whites. Here, well, obviously, they came apart. And the black is, only thing I can tell you is a black is gravity. It's attractiveness. The white is get the hell away from me-ness. And the black is, come on here, cuddle up with me. I don't know. That's all I can tell you. And they don't mind being on top of each other. But they don't come back in until these guys settle down. So something is forcing everybody apart. Everybody. At this point, everybody has to get away from everybody else. The white said, "Get away from me," and take your black guys with you. You know, they just roll away. That's all I could say. That's what I'm seeing. Now, there's a lot to think about here, why this is. And I believe there's two different ways that the electrons, and I believe a photon is nothing more than an electron back to back. Hold on one second. All right, instead of that, I'm just going to show you. You see the black ball, I said, and here's the power ball, which is the electron. Now, they just admitted this in the Royal Institute. I follow them very carefully. And they admit this is all the Bohr model, all that stuff was wrong. Now, we're going to be looking at this right now. This is the experiments I did with Rod Warren, light experiment. And I have the actual experiments. And I'm going to show you how you can do them yourself. Because you could do these, almost everybody, well, a lot of people have these things that they have cell phones. That's all you need is a cell phone. That's what these pictures were taken with. I don't know exactly how Rod got them in such excellent, it's perfectness, but he did. Now this is light, and this is light passing as a red laser. And light is nothing more than a huge ball of magnetism with a tiny little particle in the center like that. And it controls huge magnetic regions like this. And it's coming one right after the other. Boom, boom, boom. And that's wave, 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 wave. That's what we got now. So that's what we have with the magnetic balls controlling huge magnetic regions. Now, there's something called, and the reason these little glowy things are here is because they're concussing. Anytime you push and you shove back, you get glow. The most glow is the most push and shove. So here's where we have the most glow, is the leading edge of that particle's wave. The particle's back here, and the leading edge of its ball of influence is here. Boom, glow. But everybody else has to glow a little bit too. And as it comes closer and closer, they glow more and more. Now, what happens if you put a restriction in front called a venturi? This is what happens. You force the whatever's going through the venturi to accelerate. I don't care what it is, water or liquid, anything. It doesn't matter. You squirt through squirter comes out the other side, just exactly like this. So we are forcing a stream to go through there, and that stream is the particles. Exactly like I said, that particle is right back there. Well, all of a sudden we say, you got to go fast to get through there, and it starts coming out, and here it is here now. And what does it look like when it's there? Well, at this point, I believe when the particles are here, they are in that photon formation where you really have like two particles. Wow, that was reactive. It's really like you have two particles together right up in here. And they create that back-to-back poles. And then they separated here. We saw it. There's no question what we saw. Now, this is where the venturis are. I'm going to show you. You can do these your own experiments. Let me show you. This is going to be a lot of fun for a lot of people. But let me just explain the rest of this. These are the electrons. Remember we talked about the dark particles. They're on the outside. They have nothing to do with the electrons at this point. And what do the electrons look like here? They look just like this. All right, the particle is right dead center in the center, and it is creating some kind of magnetic pulsations around itself. And here's the particles again. I think we saw these at least before. Now, this is the particle I said that's not an electron, and it's not a muon. It's a mahuna. I don't know what it is. It's something that we don't know about and nobody knows about yet. Now, this is a spinning to the right particle, right-hand rule, anybody understands it. It means it's drifting to the left, spinning to the right, obviously compressed, obviously expanded, obviously slowing down, and obviously a very, very short distance right after the accelerator. Now, this is, this stuff is not very, very difficult to understand once you stop and start to think about it. Now, let me show you something here. Where is it there? Rainbow shower. Here we go. This is the one. Remember I showed you that little bitty particle? I think that's how that started. They all came through here, coming at us as red laser light. Now, here's the key. This is very interesting because it displays two things at the same time on the same picture, and I think they're pretty interesting. The first thing is, we're coming through here with red laser light. Case closed, it's red laser light. It's all coming from the same stimulated source. So they all should be the same. In my mind, that's what I'm seeing. Now, I know about the purple one here, it's literally crushed, which forces it to display a stronger signature than the other ones. You see how well, I think I explained it later, but you can see it's totally different. And the reason is it's being crushed by the other particles' fields. And I think I do show this later. But anyway, this one here that's the interesting one. I think that one is spinning backwards, literally gathering its field. And when it concussed with one of these other fields, it spit it out. It did something. I really can't explain it. Really can't. Well, a lot of things I can't explain, but that one I particularly can't explain well. But there's obviously an explanation for it. Something happened to it. And they actually have, they call it an anion. I did a video on this the other day, which means you're supposed to only have two energies, which really one of them is no energy at all. That's the dark matter, the black ball that I showed you. And the other one is these particles. And so there's one or the other. That's just it. Case closed. It's supposed to be only that now. Well, I have shown that that is not the case. Totally not the case. So this could be an anion. It's in between, because we know that when it hit, it was absolutely nothing. Hold on, let's go back. We can see this. It's not like you can't see this. I'm not making any jumps of conclusions that aren't supported by anything. Here's the little particle coming through here, and anytime, like I say, if you see the glow, everything's coming this way, because whatever concusses the hardest glows the most. It's push to shove. Now, that hit or its field became changed, or whatever happened, but I don't know what the hell it is. I gotta be honest, I have no clue. But that's the result of what happened. Now, you can see it's a spinner. Now, is it spinning right? Is it spinning left? I don't know. Why did it drop off of this field? And did this field create this field? Or is this an additional field to that field? Is it like bouncing off the edge of that field? I think now, originally I thought this created this field, but now I believe this is bouncing off the edge of this field. Like that field's spinning this way, this field's spinning that way, and it hit it like a backwards record. You know, I don't know, but it's something is re-accelerating that. Again, when you see glow, the glowier the glow, the more the impact, the more the energy. And I'm seeing this grow from whatever it was here into energy. So it's, in my mind, it's all kinds of different energies right here in this one little bazillionth of an inch. So, you know, it just shows you that there is so much to think about that is avoided. The thought process is not working well in physics. You know, they are denying, a group of deniers, really, is all I have found. Nobody's asked anything, not a question about this. Let's try it, let's see if that works, let's think about it. Nope. Stay away from us. You're a nutcase. Now, if you look up Cherenkov radiations, it's high-speed electrons, high speed, and then the muon portion, which is the black ball I will show you, creates this, nothing. It just goes to black ball. The electron portion, electron neutrino portion, creates electron showers. They splash all over, and I will show you this. These are nothing more than high-speed particles crashing into a lower, a density of other particles. Now, I think we can change the density. I think we can do all kinds of things with this that's not being done. Nobody's looking at it at all. All right, now I'm going to tell you something right now. Light is light. I don't care what anybody says. You shoot light out of a red laser, light is light. So it's the smallest particles basically that exist. We saw they were back-to-back looking particles like this. Now we're seeing that they separated. You see this? And why would they separate? They separated because there's two round drums. There's one right here and one right here. And they were literally nails. I believe Rodney Warren is the one that came up with this just by accidentally. And he had two round, I believe they were nails, and when he shot the light through that, as he was trying to do a single slit experiment instead of double slit. And when he did that, he got this, and he just was posting them online. I said, whoa. Now, you can see the particles separated. As far as I'm concerned, there's no mystery here whatsoever. And Einstein and all the rest of them were talking about spooky entanglement, and then spooky entanglement at a distance. So they're saying that black ball will come back to the white ball that it was attached to back here, down here. No. Absolutely not. It's going to come back with some other black ball, some other white ball, absolutely. However, this one's not going to go find the one that broke off it and go just find that exact one. The reason they're talking about quantum entanglement, because they're at absolute zero. Absolute zero, there's nothing here whatsoever. There's no electrons to bash into. So they shoot an electron in here and it breaks apart, absolutely. The black one's going to find that same exact white one because that's all that's here. And if, boom, they will come back together, obviously. So they're high speed, boom, and they break apart for some unknown reason. I thought they break apart because they smash into other particles. But maybe they will. Maybe they'll just slow down for the nature of resonance. And if that's the case, if you can shoot just one in here, yes, it's going to find its partner down here somewhere, but only if there's a one. And that's what's called absolute zero, and not a single extra electron in here. As soon as you add any heat and any vibration or anything whatsoever in here that creates an electron, you're done. It's all over. That's interference. And then these two will never find each other correctly again. Yeah, they might, And that's why they do like a zillion different experiments, and then they figure, well, we found 20% had the same value. That means that those were good. They didn't get interfered with. They didn't bash into any noises. They call it noise. They call it shock or something. I can't remember. But it's what all it is you bang it, and you anytime you bang anything, you push to shove. You push something against it, it shoves it back. I don't care what it is. You bang against that screen, it's going to bang back. I bang one hand against the other, it bangs back. Same thing, and it's because of electrons. One electron pushes against the other, push, push, push. I call it push to shove. And that's what's going on here, and then particles find their way back together. This is dark matter. And the only value it has whatsoever, the black ones, is to pull everybody back together. They come down here and they pull everybody back together. Right? The white ones still want to push everybody away. That's why you get these lines here. And the reason you get these lines is not because of flapping interference. This is a single slit. What it is the light spins. It spins this way underneath and goes that way. Over the top, comes off and goes this way. Most of it comes through the center. But it spins like this. Now, some of it's spinning over here. Some of it's spinning over here. It's not just one particle. They're coming all over the place. And then they smash down into that. Now, I say we can vary this. Well, what can we do? We got high-speed particles. We know we can separate them. We know the white is the explosive part. The black is simply just to bring the exploders back together. We want the exploders. If we get them together, they don't have the same value as the exploders do, obviously. You could see, once they came apart from the black ones, the energy increase is absolutely astounding to me. I could be wrong, but I don't think I am. When you see lights light up, you notice some kind of energy happened. Okay, my friends, I'm going to tell you right now, this is the extent of the tools Rodney used to do. He had a couple of other little laser guns, but nothing special. He used a Bosch GLM 15 little laser that measures distance. It's a pulse red laser. And he used a Samsung Galaxy 3 cell phone to take the images. And he used some other little lasers, but you have to be careful. When you're ever using lasers, you should get the goggles that you know, so you don't, if you hit it in your eyes, you're in trouble. Now, what am I going to display? What am I showing? And I think I show it, and I think we can enhance the effects of the things that I just showed you. I believe I showed you the particles accelerating and then smashing in here and then coming out in showers of electrons, where the black balls, which are the dark matter, and the muons went around and reassigned themselves way down the road. Now, we know this is the photon. That's the symbol for photon. Electrons have two different varieties in my world. An electron sitting stable would be the dark part of the electron would be in the center because it's a dipole, and energetic particles would surround it. And I can't give you that, but it's a field. In other words, there is, I can't tell you where a particle begins and the electron ends. But it's one little particle. Now that particle is either end to end like this, if it's attached to another particle, or maybe it'll be like that if it's in a molecule. But if it's on its own, I believe it's like this. And the entire outside edge is the fluffy white push. And I can show this in a magnet, and I will. And I'll show you uno momento. But that is what my electron looks like in electron flood theory. It's not just a negative. The negative is the fluffy white push portion, and the black center is the attractive muon particle that does nothing. And I say it's dark matter. If they're looking for dark matter, that's it as far as I'm concerned. All right, you as people at home could do the same experiments and record them. I'll show you how Rod had it set up. Now, the electrons are coming in here. If we had copper here instead of steel, I'm going to show you what copper does, or I already have shown you. It pushes back like hell against magnets, and electrons are nothing more than magnets. I'll show you that too. And when it hits there, it pushes them back. Now, that's all I can tell you is maybe if we changed the venturi and we flooded it with electrons between the venturi slot, we would get just enormous amounts of energy. Or maybe not. Maybe it would just push it back. Maybe we would have to have the venturi way up here made out of something that would have no extra electrons, and so there'd be no push to shove until it hit here, and by that time they're already sort of compacted and have nowhere to go, and they have to go through here, and they plow through like a gigantic wedge of electrons. You see, or you have seen, you drop a magnet through copper, it has to completely encase it. So it has to be both sides copper on both sides. Now, how are you going to trap these electrons when they come through? Because they come through white, just brilliant white, and the black balls come around. Well, there is a possibility of taking more copper and just continuing a dense amount of copper just right here and waveguide, and so this would be copper as well, but it would be like a chunk. So as these hit against it, they would be deflected off this way, because we know they push to shove. Now, then you would have some kind of a collection device here, you know, a capacitor type thing, you know, whatever, and guide them into there to store them, something like that. I don't know what else to say, but if I know right in this general area here, you have a brilliant, brilliant, brilliant white. To me, that is electrons, raw electrons. If you could harvest those, and you could enhance them and then harvest them, whatever you had to use to produce the light flow here, the laser, which you're going to need electricity to do that, obviously. You need some power to do that. But you're only blowing light out of here. I mean, look at this. You got I think this has like a couple of AA batteries or something. I don't know. But it's only a couple of volts. And I don't know how much power you get out of this. But you could concentrate the power of the sun to get this stuff too. It doesn't have to be made by a laser. It has to just be so powerful that into that venturi that everything's going to explode in front of it. Right now we're using coherent types of light like lasers, where you have like only one frequency, red or green or blue, that type of thing. Now, that doesn't mean you couldn't have every kind of, the whole spectrum coming here at the same time. Obviously you could do that. Why not? Why not? And maybe you could have multiple layers of venturis, big ones, and then come smaller ones, and then shoot one off to this way and one off to this way. I don't know what you could do right now. There's not been a single bit of looking at this in 5 years. This is the key with science. If somebody can't prove, or I don't know what they're thinking, to be honest with you, but it seems like it's just a big competition of who can do what and get, and it doesn't matter if it's right or not, as long as somebody says, "Ooh, that guy's smart," and then he's happy and goes along with his life and becomes the hero. And it doesn't matter what you present; they just dismiss it. Get away! No. Nobody talked to me about this. Not a single. And I even went to the University of Geneva for particle physics, and they were, they didn't want to engage. They just, wow, that's nice. I would have thought they would have taken an interest, but they said they'd follow me on Facebook or something, or YouTube. I don't know what to say anymore about how knowledge gets passed along. I think it requires examination, And if this could get you free energy, I mean, what the hell is wrong with that? Am I making a mistake bringing things like this forward? I've been bringing all kind of, and well, some of the stuff is very shocking. There's no question whatsoever about that, because it shows that the things that were in our past, a lot of them that people have thought were just silly as we went into the age of enlightenment, end up to be physically, material, factually supported. Whereas the opponents of it have no factual opposition to what I present. All they have is, I read a different book than you. Well, I didn't read a book. I looked out and see what was on the ground and what was in the chemistry and what was written, and it all matches, my friends. So this is just another side of the coin. I shouldn't have bothered going there, but that's what I do. I just jump from here to there, and this could be free energy. Could be free energy. Okay, this is a channel called Good Tim S for All. And this is about, does copper affect the magnetic field? And then somebody in the comments section said, tin foil does as well. A roll of tin foil, if you take a big magnet like that and drop it through the tin foil, it has the same sort of effect. Now, copper is here, aluminum is here, which is tin foil. And it might happen with zinc, and it might happen with nickel as well. I would like to see somebody try that. And the reason is because these are not big chunks of protons. There's a bazillion, zillion little electrons surrounding them. And these particular areas have clouds of them. They're in the transition metals area. And this one here is in other metals, aluminum and so forth. Now, but they have enormous, dense cloud of electrons. So the electrons that are coating the magnet, and I will show you those right here in magnetic tape. It will show you how a magnet affects, you'll see a cloud of electrons. The cloud of electrons in the magnet hits the cloud of electrons in the copper, and they push to shove each other. And ooh, and he will show that right now. And I mentioned to him that I would be using this video, and it's nicely done. And he's just a normal guy saying, well, how does this work? And then he's got a light box here. Let me just explain to you what a light box is. A light box is where you put a whole bunch of aluminum foil and reflecting stuff inside, and then you put a bunch of little lights surrounding the whole thing, and it's in sort of an enclosure. So you're really packing it with electrons. And the light is nothing more than electrons. Light is electrons. I showed you that. I showed you that in my stuff with the light. Now, so when he puts a magnetic field pushing to shove against the electrons, it will light up wherever there's electrons pushing back. And you're going to see stripes, just exactly like the stripes I show from the spray of electrons coming in. Now, here he goes.
Through a copper pipe.
Look, see how slow it
takes
goes?
it a second to get through there. There's an interaction between the copper and the magnet. Not quite sure why.
That's what
what's
we're
so
going to see.
special about copper, but it just takes a second for it to make its way through there. Straight up and down, I mean, you can see if I just drop the magnet, it falls pretty fast. Drop it through the copper pipe, it takes a second to get through the pipe. Now, the neat thing is that this does not affect the magnetic field. Putting a piece of copper around a magnet does not affect the magnetic field.
I want to tell you something, brother. I did not know that. I never really tried it. I never saw anybody else say anything about it. But it's very, very interesting, and it's exactly what I would have suspected, because the magnetic field in the magnet is going to push through the other electrons, and it's going to push a little more when they're surrounded by a ton of extra electrons, but it's almost exactly the same. It's just that it's pushing through the copper, which normally if you push through the copper in a tube like this and you had to go through, they're all dense in that tube. But if you just had half the tube and you dropped it, just falls straight through because everything gets out of the way. If it's dropping through the tube, it has to push all those other electrons out of the way. That's why it slows down coming down the tube.
You can see we'll lay our magnetic.
All right, now this is the light box. There's his magnet. Now, what are we seeing here? We're seeing the magnetic field. And why are we seeing stripes of light and dark? Well, anytime you see light, anytime ever you see light, that is push to shove. Push to shove. So where's the push coming and where's the shove coming? Inside this light box is dense with extra electrons. So as this magnetic field comes out, if it actually has heavy push to shove in regions, you'll see it. They'll be brighter and darker, and that's exactly what you see. So when he slides the copper over it, all it's going to do is just do the same thing, but only it's pushing out of the copper. So the copper is more or less acting just sort of like a shirt around the thing, but it's or whatever you want to call it. It's just an envelope around it that has no real effect on its direction of magnetism.
Lay it down in your magnetic lines. You have your dielectric.
I think they get thicker and more pronounced when he puts the copper on, but I could be wrong.
North, south, whichever way is which. You see the holes there on the sides. Okay. Now we will put the piece of copper around it.
You see how thick and bright they are now? It's pushing more electrons. That's what I think.
And there's your magnetic
Look
field.
at that. See how bright that is? It wasn't that bright before. There's so many extra electrons in here. As its field pushes out, it's pushing out excess electrons. That's what I'm saying. Now, and I believe that's what will happen when we put it through the venturi. Coming out the other side, there'll be so many extra ones that it'll enhance it, I believe. Now, but you can see that's some pretty serious interaction now. A little more serious.
It's the same. It's weird.
You see how it's it just doesn't have the same intensity. Now, coming down though, watch this.
No change at all in the magnetic field. I thought that was pretty cool. Just wanted to share that with you.
I don't think there was any going down either, but going down is at the poles where it wraps back up. Would you see that field change? Well, you don't see it, so that answers that.